Welcome to the Explainer. There's this invisible architect all around us. It's the reason huge steel ships can float, or how a bunch of balloons can lift a person right off the ground. It's even what makes your car brakes work. Today, we're going to pull back the curtain and make this unseen force visible.
So take a look at this. This is John Ninomiya. Back in 2003, he did something that, well, it looks straight out of a movie. He hooked himself up to 72 helium balloons and just floated away. Now, it wasn't magic, not at all. It was pure physics. And honestly, this one image, it's the key to everything we're talking about today.
So that brings us to the big question, right? How in the world can a simple cluster of balloons create enough force to lift a grown person into the sky? The secret, and this is the cool part, isn't really about the balloons. It's about the air around them. And to unpack that, we need to find our first clue.
All right, clue number one. What is fluid pressure? Before we can figure out how things float up, we've got to understand all the forces pushing on them from every direction.
Okay, so pressure, it's really just force spread out over an area. That's it. Think about the air around you, or the water in a pool. That's your fluid. And the push that fluid exerts on any surface, that's its pressure. Yeah, we measure it in something called pascals, but don't get hung up on the term. It just means how much push per square meter. And believe me, this one simple idea, it's the foundation for everything that's coming next.
You can actually feel this yourself. Think about just standing normally on both feet. You're putting a certain amount of pressure on the floor. But now, imagine balancing on just one foot. You haven't gotten any heavier, right? Your weight is the same. But because you've cut the area in half, you've just doubled the pressure on that spot. Same force, just way more concentrated.
And we use this idea all the time, maybe without even thinking about it. A sharp knife, it's all about concentrating all your force onto that tiny, tiny edge. That creates massive pressure, enough to slice right through something. And snowshoes, they're the complete opposite. They take your same body weight and spread it out over a huge area. That creates really low pressure, which is why you can walk on top of the snow instead of sinking right in.
Okay, so this brings up a really important point that most people don't realize. You know when you check your car tires and the gauge says like 32 psi? That's what we call gauge pressure. It's only measuring the pressure above what the atmosphere is already pushing on it. The actual or absolute pressure inside that tire is that 32 psi plus the pressure of the entire column of air above you. So yeah, the real pressure is way, way higher than your little gauge lets on.
Okay, on to our second clue. How pressure changes with depth. So we know pressure depends on area. But what happens when you start going down, deeper into a fluid?
Anyone who's ever jumped into the deep end of a pool knows this feeling. The deeper you go, the more that pressure builds up in your ears, right? What you're actually feeling is the literal weight of all that water stacked up on top of you.
And there's a beautifully simple formula that explains this perfectly. The extra pressure you feel is just the fluid's density, basically how heavy it is, times gravity, times your depth, which we call h. It's a straight-up linear relationship. You go twice as deep, you feel twice the pressure. Simple as that.
We actually see this principle in action in every single hospital. For an IV drip to work, the medicine has to have a higher pressure than your own blood pressure to flow in. So how do they do it? They just raise the bag. By increasing that height, that H from the formula, they boost the fluid's pressure just enough to get the medicine into your bloodstream. It's a brilliant, simple solution.
Okay, so we've got it. Pressure depends on area and it depends on depth. But now, this is where the real magic begins. This is when we learn how to control it. And there's no better example than the hydraulic jack.
So imagine you're using a hydraulic jack. You push down on the handle, applying a pretty small force. Let's say about the effort it takes to lift 10 kilograms, maybe 22 pounds. You're just pushing on this little piston with a bit of effort. So what do you think that little push can actually do?
Well, that tiny push suddenly becomes enough force to lift a 1,000 kilogram car. A car. That's 100 times more force than you put in. How on earth is that possible? The secret is all about how pressure works when a fluid is trapped or confined.
This is Pascal's law, and it's brilliant.
It says that in a contained fluid, any pressure you apply is felt equally everywhere instantly. So the pressure you create under that small piston, it's the exact same pressure now acting under that big piston. And since pressure is just force over area, if the big piston has, say, 100 times the area, it has to generate 100 times the force to keep the pressure the same. It's like a force multiplier. This is the principle behind everything from giant construction cranes to the brakes in your very own car.
Okay, so we can use fluids to multiply force. That's huge. Now let's take everything we've learned and circle all the way back to our original mystery, the man, the balloons, and the big secret of how things float.
Remember how we said pressure gets stronger the deeper you go? Well, that is the key to buoyancy. Think about it. For any object sitting in a fluid, a boat, a person, even a balloon in the air, the pressure pushing up from the bottom is always going to be a little bit stronger than the pressure pushing down from the top. That small difference creates a net upward push, and we have a name for that push, the buoyant force.
And this brings us to the grand reveal, a discovery made by Archimedes over 2,000 years ago. He asked, okay, but how strong is that upward push? And the answer is just perfect. The buoyant force is exactly equal to the weight of the fluid that the object pushes out of the way, the weight of the displaced fluid. That's it. It's a simple, powerful, and beautiful rule that explains why anything and everything floats.
So really, it all boils down to a simple battle between densities. If an object's average density is less than the fluid it's in, it floats. If it's denser, it sinks. And if they're equal, it just hangs out, neutrally buoyant. It's like a tug of war between the object's own weight pulling it down and the buoyant force pushing it up. And density is the judge that decides who wins. And just like that, the mystery of John Ninomia is solved. Helium is way, way less dense than air, so those 72 balloons displaced a huge amount of air. And the weight of all that displaced air created a massive buoyant force, a force strong enough to lift the weight of the balloons, the chair, and John himself. It was never magic. It was just Archimedes' principle on a spectacular scale. Okay, so we've pretty much cracked the case for still fluids. But what happens when the fluid itself starts moving? The rules change and things get really interesting. Let's look at a couple of quick, kind of mind-bending examples.
You've definitely seen this before. You're holding a cup of coffee in a car, and the driver hits the gas. The coffee sloshes back, and the surface tilts, right? Well, that tilt isn't random. If the acceleration is constant, the surface of the liquid forms a perfectly straight, sloped line. And the angle of that slope, it tells you exactly how fast you're accelerating. But what if you spin the fluid instead of accelerating it forward? If you spin a bucket of water, the surface doesn't stay flat. It curves up the sides into this beautiful, perfect shape, a shape we call a paraboloid. And this isn't just a cool party trick. This effect is so precise that astronomers have actually built giant telescopes using a spinning vat of liquid mercury. The spinning mercury forms a perfect parabolic mirror, all thanks to fluid dynamics.
So, from massive ships floating on the ocean, to the brakes that stop your car, to a man floating under balloons, the principles of fluid pressure, this unseen architect, are absolutely everywhere. We've shown you how to spot it, so the real question now is, where are you going to see it at work next?